Hello, everyone, and thanks for joining us. My name is El-Sharif, and I am a streaming. I'm sorry. I think there's an echo. I apologize. I'm going to start over. Hi, everyone. Thanks for joining us. My name is El-Sharif, and I am a steering committee member at ACE. ACE is a global community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We have a repository of YouTube videos that showcase authors presenting the research and practitioners demonstrating the use of emerging machine learning methods in the field. We also host social events where you get a chance to network and interact with fellow community members. We conduct workshops focused on helping participants take machine learning concepts from foundational theory all the way to fully deployed models. And we have multiple streams organized around topics. This presentation is part of our interpretability stream. We encourage you to subscribe to our YouTube channel and check out our website at ai.science. Today, we are hosting Muhammed Zafar. He goes by Rehman. Rehman is a PhD candidate at Ryerson University. His research focuses on interpretable machine learning models by combining interactive visualization and machine learning to help end users understand machine learning decisions. Rehman is also a software developer and developed various products and applications, including machine learning solutions. So he is a scholar and a practitioner. The work he will be presenting today is a code walkthrough. His paper, DLIME, the Deterministic Local Interpretable Model-Agnostic Explanations Approach for Computer-Aided Diagnostic Systems. The results of this paper were presented in a workshop on explainable AI and machine learning for accountability, fairness, and transparency, held in conjunction with ACM KDD in 2019. Before I turn it over to Rehman, I will note that his work is based on LIME, Local Interpretable Model-Agnostic Explanations. His work is essentially an approach to solve the stability issues or the lack of stability reported on LIME, where it would give you different explanations for the same prediction if you run the same explainer model multiple times. It is a very interesting presentation, and I look forward to it. He will be presenting a high-level overview of his approach, as well as a code walkthrough through a notebook, so it will be a very hands-on presentation. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. I will now turn it over to Rehman to start the presentation. Thank you.
Thank you, Ali, for hosting me again, and welcome everyone. So today I'm going to present how we implemented DLIME. We are using LIME as a base model. So LIME is, so here in this slide, I have presented a block diagram of LIME. LIME takes one instance at a time and generates random data around it. Then it is using some distance, Euclidean distance, something like that, and some equation to weight these samples. Then it trains a simple model on those instances to select its features and to provide explanations. So if the data is linearly separable, then we can train a linear model, and that is a very simple model. Linear model and decision trees are the models that are considered interpretable. Here in this diagram on right side, it is a hyperdimensional data, and it has a lot of boundaries inside it. So it is very hard to it is very hard to discriminate between these boundaries. But if we are focusing on a particular subspace or particular region, then we can generate a linear boundary between them. So for this purpose, LIME proposed a linear interpretable linear regression based model that can be used for that can be used to explain any black box model. So here in DLIME, we are not generating random perturbation. We are doing hierarchical clustering. We are using original data, so that we can generate deterministic explanations. So here hierarchical clustering will group subspaces in its region, and then we will train a KNN classifier to pick its subspace. So if we are taking instance 1, then KNN will it will compute distance from this instance to its subspace, and it will give us the best suitable subspace for that instance. And similarly, similar to LIME, we will be using weighting methodology, and we will train linear model on that subspace, and we will select features to generate visualization explanations. We tested our DLIME on 3 datasets. One is breast cancer, one is liver patient, and the third one is hepatitis patients. So all datasets, breast cancer dataset has 569 observations and 30 features. Liver patient dataset has 583 observations and 11 features. Hepatitis patients dataset has 155 observations and 20 features. So the links are in the footer, so you can go to UC archive and you can read about these datasets in detail. So breast cancer dataset looks like this. It has a binary class, benign and malignant, and then we have numerical data in a tabular form. So therefore we are using LIME tabular explainer, and once we perform clustering, we can see here in this dendrogram, it is giving us two clusters that are highly dissimilar, and we are cutting at this line so we can get subspaces. Here we are using two clusters. C is equal to 2. That means we are using two clusters because this is the largest distance. That was our threshold. And here we are training Canon, and we are only getting one instance, one neighbor. We tried with k is equal to 2 and k is equal to 3. There was no difference, so we pick 1 for simplicity. These are the evaluation matrices, Jaccard similarity and Jaccard distance, that we use to compute the stability or determinism of this algorithm. So now I will go through the code, and I will explain things there. You can download this code from GitHub repository, or if you are using Git, then you can execute this command in your console, and you can clone this repository from GitHub. So all code is there. You can download it. Here we are using some packages. So NumPy, Matplotlib, linear model, and we are splitting this data randomly. Load dataset is a custom class that gives you that contains all 3 datasets, and you can load whatever you want for your experiments. We are using a breast cancer dataset, so the URL is given for its description and more detail. Load this dataset, its feature names, and its target names. I think.
So, yeah, Rehman, are you? So, which out of the you presented your work under multiple data sets, but looks like.
I think that is some path issue.
Not.
Let me see. Look into it. Load dataset and import dataset. Yeah, it worked.
No,
okay. No. Then load dataset, which is.
So this is the liver patient data set, or the breast cancer? I think it's the breast.
It is the breast cancer data set. Yeah. So the link is provided here, so you can read its description. After loading this data set, we are going to split this. I already splitted and saved in NumPy arrays. So I'm gonna load that data set. After that, we are using a random forest classifier as a black box model from sklearn ensemble package. So here we are training random forest with default parameters because our focus is to generate stable or deterministic explanations. So we are not concerned about accuracy here. Still, with default parameters, it is getting 95% accuracy. That is good enough, I guess. So from explainer tabular, we are using LIME tabular explainer because this dataset is tabular. That's why we are choosing LIME tabular explainer. So this is the same as LIME, but I have modified it because I have a little modification because we are using um, original data. We are not generating random data, so I just replaced that code.
And with when you called Lime, did you do any changes to the parameters or optimize it in any way? Is there anything interesting about how you particularly called the Lime tabular explainer?
For this paper, I did not make a lot of changes, but for my extension work, I have made a lot of changes.
Okay.
So I'm gonna present that. Actually, I had submitted that work in a journal, so it is under review. So once it will publish, then we will have
Okay.
a discussion on that as
Okay.
well.
It's secret right now. Okay. Very okay. Not a problem.
Okay. So the next thing is we are using hierarchical clustering from uh, sklearn underscore cluster package. So this is the hierarchical clustering. We are doing clustering on training data, and we are getting its membership to filter out the local subspace of the nearest neighbor based on this membership.
And Rehman, help me understand. So the X in this case is the entire data set, or is it the training data set? What are you clustering on? Is it just the
Okay.
training?
Here X is the complete data set.
Okay.
So here, if you see, this is the X, right?
Yep. Yeah.
So we are clustering complete data, and based on the membership, we are finding its nearest neighbors. So here we are generating a new attribute, membership. We are appending this, we are stacking this attribute with cluster data, with the complete data. And after that, we are using nearest neighbor with n is equal to 1 on training data. After training it, we are getting neighbors of test data, right? So based on that label.
Okay. So maybe help me square away. So how is
Okay.
it that the clustering is on the entire data set, but then the KNN essentially is on the test set only?
Okay. So here our focus was to find membership of each and every every instance in the data set. So we created a membership attribute, right? So
Yeah.
to generate membership attribute, we did clustering on all data set. And here, when we are using nearest neighbor, so we are doing only on test data because we are working on training and testing subsets. So here, that's why we train nearest neighbor on training data, and we are picking instance of test data. So I will explain later how we are doing that.
Very good. Thank you.
We have two formulas here, Jaccard similarity and Jaccard distance. So Jaccard similarity will give you how instances are similar to each other. And for example, here list one is and list two. So this is the feature set one, and this is the second feature set. And now it is going to compute the intersection between these two. How many features are common among all features? And in Jaccard distance, it is going to give us distance 1 minus similarity. That will be this dissimilarity of the instance if it has.
So the Jaccard similarity, if you can just stick with that for a moment, it is the, can we just, yep. So it is the intersection over union, right? And
Yes.
you're just, yes, yes. So, and you're just feeding it the set of features on set one and set of features on set two, and that is enough to give you a score of similarity and differences between those two features.
Yes, we are computing this similarity and dissimilarity on 10 times actually, uh, to see if on each iteration we are getting same explanations.
Okay, okay, thank you.
No problem. Here we have a lot of instances in test set, but I am going to explain only one instance. I set x is equal to 2, so 2 here is the index of the test instance. So we have a loop from 0 to 10 because we want to compute 10 times. We want to generate this expression 10 times with DLIME and line to see how both models, both explainers are behaving. So here P level is the predicted level based on filtered C levels. So C level is defined here, clustering levels. So these are the all levels of test instance. And here we are getting this P level, and based on uh, P level will give us the indices of the uh, test instance, and then we are filtering all that cluster based on this P level. So here if it is benign, so it is gonna filter all data set that belongs to benign class that has that cluster level, right?
So help me understand this a little bit, maybe. So when we say, so we have X is the individual instance or the individual example that we are for breast cancer patient, right?
Yes.
And then you're getting the clustering labels that belong to that one particular example, right?
Yes.
Okay, so that's
So here,
yep.
here we defined clustering level. We did clustering on complete data.
Okay.
We assigned a membership column, and we stacked that column here, clustering level.
Mhm.
So each X instance has its clustering level.
Yes. Yes.
Here, C level is actually clustering levels. So we are just extracting this level into this variable.
Got it. Got it. Okay.
Here, here we are picking what is the cluster level of test instance. So
Yes.
for example, if we have two clusters, maybe it is going to give us 1 or 2 or 0 or 1, right?
Yes.
And based on that cluster level, we are filtering all the data set,
Okay.
right?
Yes.
So now n has only one subspace that belongs to this test instance.
Got it.
That is the nearest subspace of this test instance.
Okay.
So we are dropping that label thing from this because we don't need it anymore. Uh, in to explain this uh, test instance, we are passing this test instance what our trained random forest model. This is the what we want to retrieve. We actually from this we want to read probabilities from we want to get probabilities of from random forest. So if you can use random forest dot predict or random forest dot predict probabilities function.
Mhm.
So number of features that we want to read, because this data set has 29 attributes,
Okay.
29 or 30 attributes. So among them, among those attributes, those features, we are interested only top 10 features. So that are most influential. So here we are using linear regression model as a simple model. In cluster data, I am passing subset that we generated here.
Yep.
And on this data set, regressor will be linear and explainer will be DLIME. And these are the labels of data set 0 or 1. So because it is a binary data, so we are passing two labels, 0 and 1 here.
Okay.
So once we call this, once we compute this, it will generate explanations with DLIME. And it now this function explain exp underscore DLIME as pyplot to figure. So it is gonna create a bar chart. So bar chart will have two color, red and green. If linear model has written positive coefficients, then it is gonna draw green bar. Otherwise, it is gonna draw red bar.
Okay.
And then we are getting features. So what was the features that was returned with DLIME? And similarly, we are doing same stuff with LIME. We are converting explanation into image, and then we are reading its features. And once we execute this code, I think I missed some. Okay, we did this stuff, this, this, and now execute this. It is gonna take some time.
Yeah. So now, and it's doing this 10 times, right?
Yeah.
And the idea, the reason we are doing this 10 times is to compare which features were selected in each one of those 10 times. That is essentially your experiment. And just curious here, have you tried with different maybe numbers? Like, is there maybe a if this becomes does LIME in terms of just lack of stability, is it does that stability score, if you will, changes if you're doing it 10 times, 100 times, or 1,000 times, or you have not run those comparisons?
I am comparing it in my extended version, but
Okay.
here we choose 10 because we want to be fair. So if we pick 1 or 2, so that sounds unfair. So 10 times maybe it is gonna generate different or same explanations. So
Okay.
I thought 10 was good.
Okay. Okay. 10 seemed like a reasonable number, and that's
Yeah,
fair.
yeah. So here the first image is generated with DLIME, and second image is generated with LIME. So this is the first iteration. So here one thing to notice is both models are generating different subsets. The reason,
and when we're looking at this, Rehman, I'm sorry, the items on the left are just the list of features. The fact that we're seeing a range, that is just a feature that was used. It was not those were. Can you maybe explain why you're seeing the less than or equal and greater than
yeah,
sign? Yeah.
because this dataset has continuous variables, so it is discretizing this dataset into certain ranges. So that's why we are seeing this name. So name mean radius is the feature name, and then once it discretized this, it gave this name as this range. So
Yep. Yep.
so that's it, nothing else. Here in this case we are on left side we are getting we are seeing these labels. These are the parameters or feature set, and here on right side this numeric figure represents the weight of that attribute of that feature, because we are doing feature selection, so we are getting top 10 features. So based on that weight we are drawing these rows.
So
So
it would it be accurate to say that so in the case of the local the what you were looking at right now, the worst concave points greater than 0.16, the fact that that has a really long green bar, that represents the most important feature that was correlated with the prediction, correct?
yeah, that has positive correlation with the feature.
Yeah, and then the negative radius error and mean factual dimension that are shown in red,
Yeah.
those are features that are less important, but they have a negative correlation with
Yes.
predicted class, correct?
Yes.
Okay.
And here this feature set generated with DLIME and these features are generated with LIME is different. Because here LIME uses synthetic data and DLIME uses original data. So data set is different. That's why you will see a variation in these feature sets. So here one thing to notice that here in this image generated with LIME and here generated with LIME, you can see a difference. So this feature set is different from this feature set, as you can see here,
Okay.
right? So that is the instability of LIME. So for same instance, on each iteration, it will give us different feature set. So
Yeah.
that was the limitation of LIME that we are solving in this DLIME.
Okay.
And after that, um, after this result, we are going to compute Jaccard distance, and uh, Jaccard distance is based on Jaccard similarity, because the formula of Jaccard distance is 1 minus Jaccard similarity. So first we will compute Jaccard similarity, dissimilarity of DLIME.
So maybe just curious, is there and of course, so DLIME would have perfect similarity, right? Because it's deterministic and it's always
Yeah.
giving the same features. Okay.
Yes. And here, this is the you can say dissimilarity, and if this is close to zero, no, this is negative, sorry, and this is close to zero. So here you can see a color that is zero. So here, this 0 to 8, these are actually 10 features: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are 10 features. So it is computing similarity from all between all these feature
Okay.
set.
So I think we have a question from the audience. Does that mean that DLIME considered everything important, or the charts are just based on the most important features?
Sorry, can you repeat that?
Does that mean that DLIME considered everything important, or the charts are just based on the most important features? So maybe we can just clarify what we're looking at in these charts are these are the 10 most important features
Yes.
that
Yes.
DLIME selected. And
Yes.
what we're showing here is that the same 10 features were selected through the 10 or the multiple iterations that you've had of DLIME.
Yeah, that's true.
Okay, got it. Yep, thank you.
And here for LIME, here you can see 0 on diagonal. So that is the similarity with itself. And then 0 among 1, 0, 2, 0, 3, 0, 4, 5, 6, 7, 8, 9. So here you can see significant distance on each iteration.
So if we can just stick with this chart for a bit, obviously along the diagonal, right? 0 with 0, 1 with 1, those features are going to be identical, right?
Yes. Yes.
And this feature, this chart is a mirror image, if you will, if you hold it across this diagonal line, correct?
Exactly. Yes. So this thing is a mirror of this thing.
Okay. Okay. And okay, thank you.
No problem.
Is there a numeric score that was assigned? Like when you said you calculated the Jaccard similarity, are
Yes.
numeric values that you can show us, or is that maybe not in this particular code set?
Actually, those values are not in this
Okay.
notebook. So maybe these are in slides. Maybe no, no. So this graph is basically based on that similarity. Once you execute its code from Git repository, you will see that those values as well. So it will return array.
Okay, not a problem. Not a problem.
I can generate, I guess. Yes. If we print this sim function here.
Okay. Yeah, just mostly in Lime, right? When we're making, essentially, I'm curious because Lime is noted to be unstable.
Yeah.
So that array is showing us.
So this is the dissimilarity with itself, and then with one instance, second iteration, third iteration, fourth iteration, fifth iteration, sixth, 7, 8, and 9. So these are the 10 iterations. So this is row 1 in this figure.
And this is for Lime itself, right?
Yes.
Okay, beautiful, beautiful.
This represents line 1 here.
Okay, excellent. So just curious. I mean, you're mentioned that you're looking to do extensions of this work. Can you give us a sneak peek? I am dying to know what else is coming up based on this really interesting work.
Okay, the first thing is that we are focusing on the quality of these explanations. So this is a subjective. So we can say if these attributes belongs to this explanation, then it is a good. So if we involve a human, then he or she may can provide more insights why this is better, right? So, but we are trying to compute this importance quantitatively. So we are working on that. So maybe you will see in our future work how we are computing feature the quality of these explanations.
Okay. Okay.
Yeah.
So it's more human type experiments and just
Yeah.
showing them the presentation, the features that were selected, and saying, does this help you make a decision? Are the quality of these explanations good, bad, or indifferent? And you're just getting an expert assessment based on interacting with this DLIME model.
Yeah. So here, by looking at this diagram, if you look first two images, so because feature sets are different in both explanations, so we cannot rely on one model, which model is generating good explanations. So DLIME is generating stable explanations, LIME is generating explanations, but which is better? Which is high quality explanations? Which are high quality explanations? So we are answering that question in our future work.
Yeah, and that answer really is given by subject matter experts, and so if it's
Yes.
breast cancer,
Yes.
it will be
But
yeah.
yes, but what we are doing, trying to do it quantitatively.
Yes, yes, okay. Anything else? I mean, there's a lot of room to experiment with some of the parameter tuning and maybe run larger number of iterations and whatnot. Are there any sneak peeks that you can maybe potentially let us know about future work that you're building on this base research?
Actually, we are doing a lot of stuff, but
It's
it's
confidential. Okay. No, not a problem. Not a problem.
yeah,
Well, I know this is work in progress, but it definitely solves a very practical problem, and it's a very interesting approach, and definitely one of the concerns or that many in the literature have pointed out is the instability of LIME. And if I run the explainer multiple times and it gives me different explanations, well, what do I do, and which one of them is good? So definitely it's a very important and interesting area of research, and I really appreciate you sharing that with us. Is there? I mean, I think we ran through the whole code set. Is that code available on your GitHub repository? And
yes, this code is available on Git repository.
okay, so definitely we are going to be posting that the slides and the link to the GitHub repository on the event page. And are there any final thoughts or comments that you want to share with us before we wrap this up, Rehman?
Thank you, Ali. If you like this work, if someone uses this work, please consider citing our paper. Yeah, thank you.
Absolutely. Thank you so much. And to the audience, I appreciate you joining us today as well. And we look forward to being in touch with you and having another future session with you as well. Thank you. Take care. Bye-bye.
Bye.